Hi guys, we're going to be doing some similar to what we've been doing the past few streams. This time we're going to be doing number theory, sorry, not number theory, we're going to be doing counting and probability on Alcumus. So let's take a look. We'll be writing, like I'll be putting the work over here. It's just refreshing right now, 1 second. This is where I'll put the work and then, yeah, let's find some space here. So, okay, first of all, I did finish number theory, so I'll just quickly show that. I got until like here in the last stream, and then yesterday I finished off the rest of it. So we're done with that now. Let's work on counting and probability now. So we'll start. First question is this. So Jason counts up from 1 to 9, skipping the even numbers, then immediately counts down without skipping anything. So he counts down normally and then keeps on doing it. So we can just write out the first few things here, the first few terms of the series. So 1 second. So 1, 3, 5, and actually we can just find a pattern like how many numbers do you need before you repeat, and then we can simplify it from there. So 1, 3, 5, 7, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then after this again we'll start going back up, right? So actually we shouldn't write 1 over here, we should write this and then the loop, and then it'll loop over again, right? That's how it'll continue. Yeah, so basically 1, 2, 3, 4, 5. Then this is another 7, so that's 12 things in total. So every 12, there's a period, the period is 12, right? So it's got a periodicity of 12. Might have said that wrong. Since there 1000 integers, we know that the 12th one will be 12, will be 2, 24th will be 2, and so on. So we know that the basically the we need to get a multiple of 12 that's close to 1000, and one possible number for that would be, so 900 works. To 900 we can add 96. So 996 is a multiple of 12. So that will be 2. Then 997, 998, 999, 1000. So the thousandth term should be 7. I think. Not sure. Okay, yeah. So it's just correct. Okay. How many positive, even, perfect cubes are less than 2008? So it has to be a perfect cube. It has to be less than 2008, and it has to be even. So what's a cube root of 2000? What is that roughly? It's like one, what is 15 cubed? So 12 cubed is 1728. So 13 cubed will be more, 14 cubed will be a lot more. So basically we go from 2 until 12, and it's only the evens, right? Only evens. So how many are there? We can divide it all by 2. We go from 1 to 6 if you divide it by 2, so that's 6. So there's 6 perfect positive even cubes. And what we did here was we took the cube roots, which is the same because each cube root will correspond to exactly one perfect cube. Instead of finding the cubes, we just looked at the cube roots. Okay, now Venn diagrams. Ellen baked 2 dozen cupcakes, of which half contained chocolate, 2/3 contained raisins, 1/4 contained chocolate chips, and 1/6 contained nuts. What's the largest possible number of cup? What is the largest possible number of cupcakes that had none of these ingredients? Okay, so since I have 4 different things, we could try to make a four thing a Venn diagram with 4 different sides, but there's no need to do that. Let's just write it down though. So half, that 24 in total, 2 dozen. That 24 in total. Then what else? So chocolate, that's half of them. So chocolate will be 12. 2/3 contain raisins. So that will be 16 with raisins. 1/4 contain chocolate chips. So that will be 6 chocolate chip. And then what's the last one? 1/6 contain nuts. So that will be 4. So nuts are in 4 of them. Okay. So to in total, if you add it up, how many do we get? We get obviously a lot more than 24. So what if all of them, like what if um we want to maximize a number that have none of these ingredients? So we want all of them to have nuts, right? So um there'll be four that have, well, not even just that. We want, sorry, obviously all of them can't have nuts. That's only four, but we want four of them to have all of these in them. Okay, so that means four, they're going to be four cookies with chocolate, raisins, chocolate chips, and nuts. That way, all of these will go down by four, like individually, so that no more nuts left. Done. They're just, so there's one with all, and this has four in it. Now this goes down to eight, this goes down to 12, this goes down to, so it goes from six to two. Right now we do the same thing with two. How many have chocolate, raisins, and chocolate chip, but not nuts? So all except nuts. That's going to be two. So then this will go down to six. This will go down to 10. This will go down to zero. Right now, how many have chocolate and raisins? Only chocolate and raisins. So only chocolate plus raisins. We'll make this six. Then this goes down to zero. This goes to four. So now if you add it up, we've got four, 6, 10, 16, which means that a maximum of 8 that don't have anything. So it'll be 8. Okay, great. There are 20 cars in my building's parking lot. All of the cars are red or white. Also, the cars are either two-door or four-door. Great. So this one, I saw a very similar question in the AOPS book. So we can just do it like this. This is not a Venn diagram though. We can just do it like this. So red, we can just make a table. Okay, so red, white, those are the colors, right? Red and white. Two-door or four-door. So we'll just write two-door, four-door. 12 of them are red. So in total, that 12 over here. 15 of them are four-door. So 15, right? And four of them are two-door and white. So two-door and white. Uh, Four of them. And they're asking us for how many are four-door and red. So four-door and red. They're asking us for this. Okay, this isn't bad. We can put a 5 here because these two add up to 20, right? This adds up to 20. That means this is 1, and so this is 11. That's it. There are 20 players on the basketball team. All 20 are taking at least one of biology or chemistry. If there are 8 players taking biology and 4 taking both sciences, how many players are taking chemistry? Right, so basically it'll be 16 because it's the 4 people are getting counted twice. So in total, it'll add biology plus all the people are playing biology plus all the people are playing chemistry will be 20 plus 4. So it's 24 minus 8, which is 16. One day Max says to Liz, out of the 25 people taking either English or French, you and I are the only two taking both. Okay, so there are 25 people taking English or French, so there are 18 who are taking English in total, so there's 16. So basically there are 27 people using the same logic who are doing English plus who are doing French. So that's including the two people who do it. The two people, Liz and Max, they count twice. So that's 27. There are exactly twice as many people in the English class as there are in the French class. So since it's 27, it'll be 18 in the English class. But remember, there are two who are taking English and French. So that means it'll become 16 in the English class who are not taking French. Okay, done. We mastered that as well. So now we'll just look at counting independent events. Using the digits 1, 2, 3, 4, 5, how many even three-digit numbers less than 500 can be formed if each digit can be used more than once? So they have to be less than 500. So the first digit can be 1, 2, 3, or 4. That's four possibilities. The second digit can be anything. So there are five possible options for it. So times 5. Then the last digit, remember it has to be an even digit. So it can be 2 or 4. That's two options. So if you multiply it all, you get 40. Okay, a state had three letters followed by three digits as a format for license plates. In order to increase the number of plates available, the state changed the format to four letters followed by two digits. Okay, so the three digits you've got 0 to 10, right? 0 to 9, which means 10. So it'll be 26 cubed times, does this work? Yeah, times 1000, which is obviously a big number. Now instead though, it's going to become 26 squared times, sorry, 26 to the fourth times 100, and you're subtracting this off. Not 100. Yeah, and then this should be 1000. Okay, so this is what we have. Obviously, we need to simplify this somehow. So we can do that by taking out, well, let's just make sure we've done all this correctly first. There are 26 letters um, in total, that 10 digits. So it's going to be three digits. So 26 cubed times 10 cubed is the initial thing. And then they change it to four letters, two digits. So 100. Okay, so this is what we have. This is what we have to figure out now. So 26 to the fourth, we can take out a 26 cubed and 100. Right, we can just take that out. So we have 26 minus 10, which is what, 16. I think that's correct. Yeah, 16 times 100 times 26 cubed. This is what we have. Now, what is 26 cubed? It's 76 times 26, right? So I'll do it like this. When you multiply, this becomes a 0. This becomes 12. This becomes 36 plus 14, so 50. This becomes 54. This becomes 36. So 6, 7, like this, 5. This is 7. This is 1. And then if there was anything here, you'd put that over there. But this is what we have. And this seems right. Now we just have to multiply this by 16 and then add two zeros at the end. And then what is this times 6? So we just multiply it by 6 basically. Wait, let me check if you can even see all this stuff. Oh, I've been covering part of it. So let me move down here. 1 second. All right. Yeah, so we've got this. That's multiplying it by 10. Now we just add what happens when you multiply it by 6. So 36, 40 to 45. That leaves you with 4. 34, so 3 over here. 40 to 45 again. So 4, and then this becomes 10. Perfect. So we've got 1, 0, 5, 4, 5, 6. Add these up, you get 6, you get 1 here, then you put the 1 over there to get 2, carry over 1 again, carry it over again, 8, 2, then 2 zeros. So 2812, 281216, 28121600. That's what the thing is. 281216, 28121600. Okay, good. A professor is assigning grades to a class of 10 students. As a very kind professor, he only gives out A, B's, and C's. How many ways can the professor assign grades to all his students? So each student can get A, B, or C. So that's 3 times 3 times 3 times 3, 3 to the 10th. Okay, great. They're letting us put this in. So 3 to the 10th. Express this as a common fraction. So 7 plus 7 8 factorial, 8 factorial, 6 factorial, 7 factorial. Fine. So here we have 7 factorial plus 8 factorial divided by 6 factorial plus 7 factorial. So obviously we don't want to actually evaluate all of this stuff. So we can take out a 7 factorial. We get this. In the denominator, we take out a 6 factorial and we get this. Now this cancels with this to give us just 7 in the numerator. So now we have 9 times 7 over 8, which is Simply 63 over 8. Find the last two digits of the following sum. The last two digits. So basically we can, okay. 10 factorial will obviously end in 00. So all we care about is 5 factorial. That ends in, it's 120. So it ends in 20. Everything else, the 10 has a 2, 5, and 10 in it. So it'll be a multiple of 100. And so will everything else. So it's just 20. Find the largest prime divisor of this. It should just be. See, I was about to say 11. Well, yeah, I was about to say 11, but notice that it's 11 factorial times 13. So it'll be 13 instead. A standard deck of cards has 26 cards which are considered red and 26 which are considered black. In how many different ways can we choose two red cards from the deck? So it's 26 times 25. That's 625, so 650. On the student government ballot at some name Deuceville, I don't know what the name is. So high school, the six candidates for president are listed first, followed by the four candidates for vice president, followed by the five candidates for treasury, and ending with the three candidates for treasurer. In how many ways can the candidates be listed on the ballot? So it's going to be 6 times 4 times 5, so that's 3120 times 3, 360. If you just multiply it. Okay, I did that wrong then. 6 times 4, 6 candidates for president are listed first, followed by the 4 candidates for vice president. So that's 6 times 4, 24. Followed by the 5 candidates for secretary. So that becomes 24 times 5, 120. Ending with the 3 candidates, 120, 360. 1 second, let me just check that. The 6 candidates for president. So that'll be 6. Oh, sorry. No, not 6 times 4. That's completely different. It'll be 6 factorial because there's 6 factorial ways to arrange them. Times 4 factorial times 5 factorial times 3 factorial. So this, I didn't want to do this, but okay, let me move my camera again because I'm blocking the work over there. Never mind, 1 second. I'll just go over here for now. This is what we have now. Okay, so we've got 6 factorial, which is 720 times 120 times 6, because 3 factorial is 6, so it's 720 times 720. 4 factorial meanwhile is 24, so it's 720 times 720 times 24, which is just, so we can now take out 100 from this to make our work a bit easier. What I want to do is get two 3-digit numbers and then multiply those. And then multiply those, then multiply by 100. So to do that, I'm going to write this as 24 times, like 24 times 9 maybe, times 8. Okay, so it's 24 times 9 times 8 times 72. 24 times 9 is just, what is it? It will be 240 minus 24. So this is 216. 72 times 8 is 560, 576. Yeah. Okay, so 576. And then we have to multiply those. I don't really want to do it. Let me try it and see if they accept this. Actually, no, let's not. I think they'll just give a 0 for that. So 576 and 216. 576 and 216. We're multiplying these. So this is the way to do it. 10, 14 plus 5, 19. 7 times 6, 42. So 49 over here. Okay. 6 times 8, 48. And then 36 over here. So 6. This becomes 11. So you put 1 here and 1 here. This adds up, these two add up to 13, 14. So again, you put 1 here. Again, you get the same for thing here. Sorry, what? Yeah, you get 4 here again. Carry over another 1. This becomes a 2. And then you've got 1 from there. So this is 1. 124416. 124416. 124416. 1, 2. And then there are two zeros at the end. 124416. 124416. Okay, good. Correct. Done with that. One more. Call a set of integers spacey if it contains no more than one out of any three consecutive integers. So what does this mean? Call a set of integers spacey if it. Well, let me move my camera once more. Actually, I think it's in the way. So I'll move it down here. Okay, that's fine. Call a set of integers spacey if it contains no more than one out of any three consecutive integers. So 1, 2, 3. Okay, well, what they when they say case for counting that, um, so basically, okay, you can have the null set, right? With zero terms, you can there's one way, just have nothing. With one term, you can have any number from 1 to 12, so that's 12. With two terms, whatever the first number is that you choose. Actually, no, I don't think this is the right way to go about doing it. We need like because that's too many cases. It's 12 cases, and that's too much. So instead, let's look at it like this. There are 12 numbers, right? You can't take any consecutive number. So no more than one out of each. Wait, give me 1 second. I'm getting a call right now. Sorry about that. I'm back now. I also had to charge my computer. I just realized. So I'm doing that as well. Anyway, now let's continue. One second. Where were we? We were calling an integer, calling a set of integers spacey if it contains no more than one out of any three consecutive integers. So 1, 2, and 3. Hi, guy from call center. Okay, so what are some possible ones? You can have like any of the numbers there. You can have 1 and 3, that would work, but well, 1, 2, and 3 is a set of consecutive integers, right? So I don't think that works then. So maybe all the numbers have to be at least 2 apart, right? Like 1 and 4 will work because 1, 2, and 3 is a set, 2, 3, and 4 is a set. But 1 and 4 can never be in a set of 3 consecutive integers. So they have to be 2 apart, right? So you can have like at least 2 apart. You can also have them be 3 apart. So let's say we start the 12 spots, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let me check that you can see those. You can. So we can go here. I'll just draw like a circle here. Then you can go here. Then you can go here. Then you can go here. That's it. Then you can obviously shift this entire thing over. So when you want four possible things, right? When you want four possible numbers in it, then you can either have this configuration, you can shift it over by 1 to the right or shift it over by 2 to the right. That's not all though, right? So that gives you three possibilities. Besides that, you can also shift, like if you keep it like this, you can remove this arrow. You can shift all of these to the right, or like you can shift this 1 to the right or 2 to the right. Um, or you can shift this 1 to the right and this 1 to the right and this 1 to the right. Again, wait, this seems like there are just too many cases. If you just want, so okay, we know this just seems like it's getting more and more complicated. We aren't really finding any smart way to go about doing this with 1 and 0. So with 0 there's only 1, with 1 there are 12 different ways. If you've got 2, you've basically got okay, maybe we can use combinations or that sort of stuff for this. With 2, you have 12 choose 1, so you can put the first one anywhere. If it's on an edge, like if it's here, here, or here, we have to have three different cases for that, right? So if it's on the edge, then you've got there's a there are two ways to have that. You can be on this edge or this edge, and then you have nine other spaces, so 2 times 9. Plus, if you're here or here, then that becomes 2 times for the other one. It can be in 8 different spaces. It can't be in any of these four, so it'll be 2 times 8. Plus, what are the remaining ones? The other ones are just, they're like 6 of them. Sorry, not 6. There are 8 more possibilities, so it'll be 8 times. And there you're taking up 5, so it can be anywhere in the other 7 places. Now with 4, now again with 3 we can do a similar type of thing. But now there'll be a lot more cases. So I don't know. With 3 there are way more cases because now you have to also worry about where you want to put the second dot, right? Where you want to put the second circle. Let's see if we're able to do it. Then we can go on to do 4 as well. So if you put the first one in any of these corners, Then there are, but see, it becomes too complicated. Like, what if you put one over here, then you put the third one over here? Now you can't go here, 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 or here. So then there are only four spots left. There are just too many cases here. So I don't know. Um, can we do like complementary counting? Complementary counting is probably harder because this is no more than one. So either you have zero or one. If you do complementary, then you have to subtract. It's harder to do the complementary counting than just actually count it. So we won't do that either. This could be something to do with like just how to pick subsets. Maybe it's some special case of that, right? Because you have, says case for counting, so it shouldn't be that bad. You know, let's take a break. Let's move on to complementary counting for now. Just take a look at this and see. What is the thousandth term of the sequence? Okay, 2, 3, 5, 6, 7, 8, 9. That are neither squares nor cubes nor perfect fifth powers. So, how many numbers are there that are squares, cubes, or perfect fifth powers? It'll roughly be, so okay, when you until 1,000, there are like 30 of them. There are 30 squares. There are 10 cubes, and they're like probably I don't know, like four fifth powers, roughly that much. So 30, 40, 50, roughly 50, a bit less. So our number will probably be around 1040, roughly that much, right? Like roughly 1040, just as a starting estimate. Now we need to look at how many things there are, right? How many squares, cubes, or perfect fifth powers there are. Remember though that obviously there's some that are repeats, like a fifth power. 2 to the 10th is both a square and a fifth power. So 2 to the 10th will fall over here. So we need to figure out how many squares are there, how many cubes are there, how many fifth powers are there. Then we need to subtract off how many squares plus cubes are there, how many squares plus fifth powers are there, and how many cube plus fifth powers are there, which shouldn't be too hard. And then we add back how many are squares, cubes, and fifth powers. And I don't think there are any of those. Because for that to be the case, you have to be of the form a to some power b, and b has to be um, a multiple of 5, 2, and 3, 15. And 2 to the 15th, so there are none of these. Basically, we already know that this is 0. So we can ignore this completely. How many are there that are squares now? Until, until 1040. The number of squares here is going to be, so 32 is 1024, 32 square, which means that they're going to be, and then 33 squared will obviously be quite a bit more than that. So that means that the number of squares is 32. Now, how many cubes are there? 10 cubed is 1,000, 11 cubed is like 1331. So they're just 10 cubes. And how many fifth powers? We can go until 2, 4. So I think 4 to the fifth. And 4 to the fifth will end up being exactly this. So 4 to the fifth. So that we'll worry about that later. 4 to the fifth. So there are 4 like that. Okay, now how many are squares and cubes? That's basically how many are there that can be raised to the, how many things are there that are sixth powers? We have 1, 2, 3 to the sixth, not 4 to the sixth. So there'll just be 3 of these. How many are there that are squares and fifths? There's just going to be 2 of them. 2 to the 10th. 1 to the 10th and 1 to the 10th and 2 to the 10th. So it'll just be 2. And then cubes and fifths, they're none of, wait. Cubes and fifths. There none of those. There's just one of those, right? That's one again. And now one seems a bit weird, but oh wait, never mind. We do have to add back one, okay? Because remember, there is one power of 15. That's 1 to the 15th. And since we've gotten a one here, one here, one here, one here, one here, one here, these three and these three cancel out. So obviously we need one more, right? So we'll add that in there. Now this is how many numbers we have. So this becomes 42, 46. Um, right? So 32, 42, 46 minus 6, 40, 41, which is perfect. So that means that there are 41 of these. So it's 1040 minus 41. So that would be 999. So we're like right there. So the next number that would work would be the thousandth term should just be 1041. Okay, great. We got it. Um, yeah. Okay, not bad. The inhabitants of the island of Jumble use the standard Kobish alphabet, 20 letters A through T. Each word in their language is 4 letters or less, and for some reason they insist that all words contain the letter A at least once. At least means complementary, but obviously we've also got the name of complementary counting here, so we have to use that. But basically, do we have to do casework here as well? Because it's 4 letters or less. So let's do that then. When you've got 1 letter, 2 letters, 3 letters, or 4 letters. Right now, the thing is with 1 letter, there is only one word. It's just A, right? With 20, sorry, with two, it'll be 400 minus 361. This is how many words there can be formed in total. This is how many can be formed without any A's. Right, so that's 20 squared minus 19 squared. This will be 20 cubed minus 19 cubed. 20 to the fourth minus 19 to the fourth. And then obviously this is just 20 minus 19. I guess we could have written it like that as well. This is equal to, from like, we can do an expansion. Um, we can do an expansion here. This is obviously just going to be 39. Okay, not bad. This one is 20 minus 19 times 20 squared plus 380 plus 361 plus 19 squared. I'll write it out, 19 squared. So this is, so we've got 1, we've got 39. Over here now we've got 20 squared minus 19 squared, which is, well, 20 squared plus 19 squared times 20 minus 19 times 20 plus 19. This becomes 1. This becomes 39. This becomes, what does this become? This becomes 400 and 380, 361 plus 400. So that becomes 761. So that's already a lot, right? Meanwhile, over here, this is 1 again, so that cancels out or whatever. Here we have 400 plus, again, that, so 761 plus 380, which becomes, so this is a 1, this is a 4, this becomes 11. So 1141, okay. Let me just check that actually. I want to be sure that that's correct. Yeah, 1040. Yeah, okay, that's fine. Now this one is a bit longer. So 761 times 39. Let's scroll down a bit. Actually, let's add up everything else. 1 and 39 become 40. Adding that here, we get 1181. So it's 1181 this far. What about here? 761 times 039. So this becomes 7. Sorry, the first digit will be 0. Then we have 21. Then we have 0, 18 and 63. So 18 plus 63 is 81. This becomes 3 plus 54, so 57, and then 0, 9. Great. 9, 7, 6, 9, 2. Does that make sense? Yeah, it seems reasonable. So we have to add all these up now. 29679 plus 1181. Let's do it. So 9 plus 1 is 10. Carry that over here. This becomes 6. One more over here. 8. So that becomes 10. Yeah, then we put a 1 there. 8, 16. Put a 1 there. And then over here, what do we get? We get 8. Yeah, that's it. And this is 0, 3. 30860. 30860. 30860. Okay, good. And that is exactly what they did. They did different cases as well. So that's nice. In short, bingo. Okay, this is a long question. Very long. So in short bingo, a 5 by 5 card is filled by making by marking the middle square as wild and placing 24 other numbers in the remaining 24 squares. Specifically, a card is made by placing 5 distinct numbers from the set 1 through 10 in the first column, 5 distinct numbers from 11 through 20 in the second column, 4 distinct numbers, 5 distinct numbers, and then 5 distinct numbers again. Okay, makes sense. One possible short bingo card is this. Okay, great. To play short bingo, someone names numbers chosen at random and players mark their cards and numbers. A player wins when he makes 5 in a row, horizontally, vertically, or diagonally. I don't know if you can see it, so let me move the camera again. I'll move it like to the corner there. How many distinct possibilities are there for the values in the first column of a short bingo card? Okay, so we have to choose any 5 of them, right? This isn't really, I don't think this is complementary counting because the first 5 are basically just going to be, in fact, isn't this just a permutation? I think you can just do that 10 times 9, so 10 times 9 times 8 times 7 times 6. That should just be it because it's basically just, what's it called? Yeah, you pick one of 10 numbers times 9 times 8 times 7 or whatever. So this becomes 42. This becomes 72. 42 times 72. So you have, so it ends in a 4. Then you have 2 over here. No, wait, what did I do? Ends in a 4. Then after that you have a 2. Then you have, so then you have a 0. And then you have 3. I think that's what it is. And then you multiply it by 10. So it should be this. Okay, good. I tried to do it in my head, so I was a bit worried that the calculation would be wrong, but it's fine. So, okay, that was a review problem. That's why it wasn't complimentary. Alyssa has 4 marbles, a red one, a blue one, a green one, and a yellow one. In how many different ways can she form a set consisting of some of the marbles if she must choose at least one marble? Um, so it's just, oh yeah, you can do, wait, this seems weird again. Like, okay, it does not matter in what order she chooses the marbles. She must choose at least one marble. Right, so okay, complementary. How many ways are there for her to choose like whatever marble she wants? So that's just 2 to the fourth. Is a red one in it? Is a blue one in it? Green one in it? Yellow one in it? So that should be 2 to the fourth minus the case where it's just one, right? Where it's just one of them, which means you're removing the case where there's 0, which is there's only one way to do that. So it should just be 15. Okay, good. It seemed a bit weird, but fine now. How many positive 3-digit integers contain at least one 3 as a digit? but do not contain 5 as a digit. So the complement of this will be that there is, wait, okay, wait, the complement would, I don't know how to do that because you're basically trying to do the opposite of that. But that could be having zero threes. That could mean having zero threes and not containing a 5, or having zero threes and containing a 5, or having um a 5 and having more than zero threes. Right? So I think it's better we won't do complementary counting here. It might be a longer way, but I think it's easier to just do it raw, I guess. So 3 digits here, right? Um, we can have this be 3, in which case these other two can be like basically anything except 5. So that's 81. And I know that this is allowing you to have 3 here or 3 here. That should be fine though. Or you can have 3 here, and again this will be 81, except, one second, except over here you can't really have, this can't be 0, so this will just have 8 options. So 8 times 9, so this gives you 81, this gives you 72. And then same thing, the last one with you having 3 here will give you 72 again. Now you have to subtract off the possibilities where you have 3 3 blank, right? This is 9 possibilities. You have to subtract off 3 blank 3. Again, here you have 9 possibilities, and you have to subtract off this, which gives you 8 possibilities, and then you add back if you just have 3 3 3. So I think that's right, at least, not sure. It'll be 81 plus 72 plus 72 minus 9 minus 9 minus 8 plus 1. So in other words, this becomes 72. The plus 1, we'll move that here to make it minus 8. Right? So now it's plus 64 plus 64. So 72 plus 128, which is just a nice even 200. Okay. Let us consider the number of 3-digit integers that do not contain 3 and 5 as digits. Let that do not contain 3 and 5. Okay, whatever. I think they obviously did it using complementary counting, but it's fine. Um, how many positive 3-digit integers less than 500 have at least 2 digits that are the same? Okay, so in other words, we can, how many do not, first of all, wait, positive 3-digit integers less than 500. So that's great. The first one, first digit can be 1, 2, 3, or 4. So the first one is 4. Wait, what? Positive 3-digit integers less than 500. So there are 4 possibilities for this. Then there are 10 for this, 10 for this. So that means there are 400 in total. Now we subtract out the possibilities where everything is where every number is unique. So that will be 4 times 9 times 8. So that's 4 times 72. So it's just 4 times 100 minus 72. Oh, I realize I'm covering it all, so let me move out a bit. Okay, that should be good now, I think. 4 times 28, which is 104. No, 108. Wait, 112. Okay, done. Finish that. Uh, oh, case for counting. What happened there? We leveled up there somehow. Wait, let me see what happened there. Complementary counting. So we wait. Where's the question about spacing or column number spacing? What happened there? Was that in constructive counting? No. Okay, something happened. I didn't mean for any of that to happen, but apparent. It seems now that we have leveled up in case we're counting as well. So I don't have a problem with that. I'm fine with that. Let's go and do constructive counting now. A play has two different roles that must be played by a child, two different roles that must be played by an adult, and two different roles that can be played by either a child or an adult. If five children and six adults audition for the play, in how many ways can the six roles be assigned? Different roles must be played by different people. So there are five children, six adults. Five children and six adults. Okay, wait, I think I got an idea on how to do this. So the first two have to be filled by children. The second two, first two, second two are arbitrary, but basically these two have to be by children. These two have to be by adults, and then these two have to be from either of the people, right? So over here we have to pick the people for this. It's just five choose two. For this, it's going to be six choose two. The number of people that are left, there's seven people left. Now it doesn't matter whether they're children or adults, right? It's just seven choose two. Like we don't care if they're children or adults. It can be either. So it's now to simplify this, it's 5 times 4 over 2 times 6 times 5 over 2 times 7 times 6 over 2. All of these will simplify a bit. 3. So this is 15 times 21, and then this is 10. So 15 times 21 is 315. So 3150. 3150. Okay, wait. Okay, so I don't think I can do. I'm not supposed to choose then. So 3150 is what we put in. Let me check if the calculation is correct. 20 times 15 will give you 300 plus 15, so 315, 3150. So that part is correct. The only thing is when they say different roles, then I guess they mean literally different roles. So we have to multiply this by 8. So this will become 0, this will become 0, and 12 carry over. Sorry, no. What did I do? 40, so 4 carries over, 8 to 12, 125. So 25200. 25200. Just multiplied by 8 because we ended up dividing each of them by 2. Yeah, and they did the same thing as us. How many different positive integers divisible by 4 can be formed? So how many different positive integers divisible by 4 can be formed using each of the digits at most once and no other digits? 12 counts, but 512 doesn't. So we can have the last two digits. There's a finite number of possibilities for that. You can have 12, you can have 24, you can have 32, and that's it. So for the last two digits, there are just three possibilities. And you can put whatever else you want, right? Besides that, so you can use each digit at most once. So obviously two digits will get taken up here. Right now, it's up to you. Do you want to include any other digits here? In these two places, you've got two digits, um, which means for each of the digits, that you can either include it or not include it. So that should give you 4. You can have, for example, let's say that you ended in 24. Then you've got a 1 and 3 in front, right? 1 and 3. So you can either have 1, 3, 3, 1, just 3, or just 1. So that will give you 4. So 4 times 3 for a total of 12. Never mind. Wait, there's also the possibility that you choose neither of these. I forgot about that. So yeah, basically you can have 13, you can have 31, you can have just 3, just 1. Or you can have neither of them, which means nothing. So that's 5 times 3, 15. I think that should be the answer, 15. Never mind. 3 two-digit integers. So what's the thing that we're missing? The only one-digit integer. Oh, that I think that's what we missed. We assume that you have to have the 3 at the end. right? And integers divisible by 4. So the 15 part we got, 12 plus 3 we got that, but we just missed that you can have 4 as well. So that's what we got wrong over there. Okay, that's fine. On the Saturday uh of a weekend softball tournament, Team A plays Team B and Team C plays Team D. And on Sunday, the two Saturday winners play for first and second places, while the two Saturday losers play for third and fourth. There are no ties. One possible ranking of the team from first place to fourth place at the end is ACB, ACBD. What is the total number of possible four-team ranking sequences at the end of the tournament? So in the beginning, you have either ACAD or BCBD, right? So how many possibilities are there? There are four possibilities. It's not 4 choose 2. That's 6. So you can't have A, B, or that. It's 4, 4. So there should be 16. There are four ways to pick the first two because it'll be the winners from each round. So it's either A and C and A or D. It's either AC, AD, BC, or BD. And it's the same thing for the last two. So it'll be 4 times 4 for 16. Okay. Find the number of four-digit numbers where the second digit is even and the fourth digit is at least twice the second digit. So second digit is even, and the next one is at least. Wait, at least or okay. So obviously the first digit can be anything, like any one of nine possible numbers. The second one can be we'll get to that later. Third one can be any of 10 possible numbers, and the fourth digit has to be at least twice that. Right? So that gives us 90. Now we have to do the case by case. Over here, if you've got a 2, well, no, if you got a 2, what are the possibilities? You can get a 2, you can get a 4 because it has to be even. You can obviously also get, so wait, you can get a 0, 2, or 4. You can't get 6 or 8 because then having at least twice that is impossible. With 0, it has to be at least twice that. At least twice of 0 is just 0 through 9. So this gives you 10 possibilities. This will give you anything from 4 to 9, which is, what is that? Um, that's 6, right? Yeah, that's 6. And then this gives you either 8 or 9, right? Because so that gives you 2. So if you add these up, these are basically the possibilities from here to for these two. So that gives you 18. So it's 90 times 18, 1620, 1620. Okay, great. Mastered that skill over here as well. Counting with restrictions. Mr. Reader has 6 different Spider-Man comic books, 5 different Archie comic books, and 4 different Garfield comic books. When stacked, all of the Spider-Man comic books are grouped together, all of the Archie comic books. And how many? Okay, so they're all like oriented the same way. In how many different orders can these 15 comic books be stacked? So you can have the Archie books at the bottom, then the Garfield books above that, and then the Spider-Man books. Or you can, so basically there are 3 ways that you can stack each of the groups. So that's 3 factorial. Then we multiply that by the different ways to do each of them. So multiply by 5 factorial, multiply by 4 factorial, multiply by 6 factorial. 3 factorial times 5 factorial is just 6 factorial again. 4 factorial, yeah. So this is 720 times 720 times 24. 720 times 720 times 24. And I think we had that exact same thing in another question. 720 times 720 times 24. I'll just scroll up and see because I'm like pretty sure we had one of those. 720. I think it's this one, right? 720 times 720. So we did 72 times 72, which gave us 576. No, wait, that's 24 times 24. And then we multiplied. I think that was slightly different actually. So this seems wrong. let's just do it. It's just extra math practice, so there's no harm in doing that. So it's 72 times 72 multiplied by 100. Oh yeah, so and then you take out a 9 from one of them, I think, right? Oh wait, yeah, 216. You take out a 9. This becomes 8. This becomes 576. So it is 576 times 216, right? You take out a 9 to make that 216. You put an 8 there, so 576, and then you add two zeros. So it is that one. Never mind. I'm not going to practice more then. I'll just put this answer in directly. 124,416. 124,416,00. Yeah. Okay. A house with a square floor plan is to have each of its four outer walls finished with brick, stone, stucco, or wood. Um, so four outer walls, meaning okay, if no two adjacent outer walls are to have the same finish, in how many ways can the house's walls be constructed? So the first, the, like when you're looking at it, the first side can be anything, right? It can be literally anything. So there are four options for that. Then the other two can't be that. So they have three options each. If both of them are the same, now if both of them are the same, you can have. uh, let me let me just check the Olympic Games medal updates. China's winning again. They're still winning, but America has more medals than. I'm just disappointed by India because it's. I know they're bad at the Olympics in general, but this is actually just terrible. Not a single gold medal, only three in total. Anyway, four times three times three. So wait, I think we have to do some case work counting here. Just like some. Okay, let's do four times three. Right now, in one of the cases, so you've decided the wall in front of you. Let's say you've decided the wall to the right of you. If the left wall is the same, then you just have three options for the wall at the back. Or if the other wall is something else, that means it's got two options. It can't be the one opposite it or the one adjacent to it. Then the other one will, then the wall at the back will also have two options. So this gives you seven. So 4 times 3 times 7. 21 times 4, 84. Okay, great. Done with counting with restrictions. Now counting with symmetry. So a regular 5-pointed star, you can rotate it, right? Actually, let's ignore that for now. Let's go to something that's a bit easy. Basic combinations. Let's just try to get some more blue stuff here because we're not doing too badly, but I just want to do some fast stuff. Some we need to divide into two teams of five for an intra squad scrimmage. So it's just 10 choose 5, right? This is like mostly just calculation, I think, at least this specific unit. So 10 choose 5, 10 times 9 times 8 times 7 times 6 divided by 5 times 4 times 3 times 2. So 5, well, let's keep the 10 actually. No, we can't. We have to remove that. So this becomes a 2. This is gone. This becomes a 2. So it's 63 times 4, which is 240, 252. 10 players, you need to divide into two teams of 5. And then the other team will automatically be decided. So let's just see what I did wrong. 10 times 9 times 8 times 7 times 6. 5, 4, 3, 2. So those cancel out. 2, 2. So it's 63 times 4. 240, 252. Okay, what's wrong here? Isn't it? Our basketball team has 10 players. We need to divide into two teams of 5. Yeah, it should. Wait, unless I'm being like very stupid about this, this should be right. It should be 10 times 9 times 8 times 7 times 6 over 5 times 4 times 3 times 2. So I cancel the 6 with this 6. I cancel the 5 with the 10 to give me 2. And I did 4 and 8 to give me 2 again. So it's 18 times 14. 18 times 14, this is 1, 12, 32, 252, 252. Okay, how is this wrong? Like, it's just, or what is it? Is it like maybe into two teams of 5 for an inter-squad scrimmage? It's just 10 choose 5, so I don't know the problem with that. 10 times 9 times 8 times 7 times 6. How is this wrong? Wait, if anyone else is here, like, what do you think is wrong in this? Did I calculate it wrong, or am I going about it the wrong way? Just write in the chat what do you think. Because, okay, let's just check. What is 10 choose 5? 252, yeah. So then obviously I'm doing that wrong. Oh, maybe you multiply by 2 because they're two different teams. I guess that's it. So 504. Oh no, I was supposed to divide by 2. Never mind. Not off to a good start, but it's fine. How many possible distinct 5 card hands can be dealt from a standard 52 card deck? The order doesn't matter. So this should just be 52, 52 choose 5. And I think it's fine. We've done a lot of calculations already. Let's just see what that is. Let's check if the answer is right. Okay, let's just see that. 52 choose 5. That should be it. Okay, yeah, and like I'm pretty sure they used a calculator as well. Uh, one seventh grader and three eighth graders. If there are four and six, in how many ways can it be filled? So it's four choose one, which is four, times six choose three, which is six. Six choose three is 20, right? Six times five times four over 620. So 80 ways. Okay, good. How many paths are there from C to D? So how many moves do you have to make in total? It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 10 choose 4, or 10 choose 6 is probably easier. 10 times 9 times 8 times 7. So this is, now you divide it by 4 times 3 times 2 times, that's it. Right, so the 4, oh wait, did I just, times 8. This is 8 and this is 7. I don't know why I put 6 over there. 4 and 2 will cancel out with the 8. The 3 will make the 9 a 3. So it's just 210. During a party, a total of 78 handshakes occurred. So it's basically 78. There's a formula for this, right? N times n minus 1 over 2. So multiplied by 2. That gives you 156. So what would be slightly higher? That's 13. So there are 13 people. 13 times 12 over 2. Suppose we want, oh, okay, same thing. So 7 and then 7 choose 3. So, or what's easier? 7 choose 4, right? So it'll be 7 times 6 times 5. So 35. Because we're dividing by 6. A teacher wants to arrange 3 copies of this and 4 copies of that on a bookshelf. all the copies of each book. So that will be 7 factorial divided by 3 factorial divided by 4 factorial. So wait, that's just 7 choose 3. That's interesting. Okay. So it becomes 7 times 6 times. Oh, again 35. So 30 choose 27. So 30. Okay, this is like the better stuff, I think. 29 times 28. Except now you have to divide it by, what is it? 3 times 2. So it becomes 10. And then this becomes 14. So what's 29 times 14? Now, obviously, for this, I'm not going to use a calculator because it's literally just computing things. 8, 17, 36. So 603, 306. Oh, I should have done that. Wait, no, not 306. Sorry, 406. I could have done that with 420 minus 14. So 406, 4060. What is n? So that will just be 1. 14 times 13 times 12 divided by 6. So this is 2. 14 times 13 is 169 plus 13, 182. Yeah, 182. 182 times 2, 364. Okay, 5 choose 3. 5 times 4 over 2, so 10. Compute 8 choose 6, so that's 8 times 7 divided by 2, so that's 28. Compute, that's just 9, right? 16 choose 5, so 16 choose 11. 16 times 15 times 14 times 13 times 12 divided by 5 times 4 times 3 times 2. I know it's written wrong here, but okay, let's do this. This is what we have. 16 times 15 times 14 times 13 times 12. Wait, I hope you can see it. Yeah, you can. So 16, 15, 14, 13, 12, 5, 4, 3, 2. 4 and 3 will cancel out with the 12, but what do we want to do? Yeah, let's remove that. Let's remove the 12. That takes care of all this stuff. Let's make this a 7 because that's easy to work with, easier at least. 5, and then let's make this a 3. So then this becomes 48 times 91. 48 times 91. 48 times 91, that's it. So this is 36. This becomes 72, 76, 08. So 8634, 4368. Good. Done with that. Now we'll continue with this thing. John has 12 marbles of different colors, including one red, one green, one blue. In how many ways can he choose the 4 marbles? Oh, can he choose 4? If exactly one of the chosen marbles is red, green, or blue. So you can choose the red one. You can choose one. So okay, you just pick. Do you want a red, green, or blue one? So that's 3 times, and then what's left? It's 9. Choose 3 because you don't want any red, green, or blue now. So that 9 things left, and you just want to choose 3 of them. So 9 times 7 times 6 over 6. So 9 times, sorry, 9 times 8 times 7 over 6. Uh, okay, sorry, 9 times 8. I don't know why I do that. We can cancel out the 6 to make the 3 times 8 of 4. So it's 63 times 4, which is 252. Okay. Amy's grandmother gave her 3 identical chocolate chip cookies and 4 identical sugar cookies. In how many different orders can Amy eat the cookies such that she eats chocolate chip cookie first? Uh, Okay, they're all identical. So you can, or both. Okay, we'll have to do some casework or whatever here. Three, so there are three chocolate chip cookies and four sugar cookies. So either you put the first one chocolate chip cookie in front, right? Then you've got basically you've got six things left, and they're four and two. So you do six choose two. So it's six choose two. It will be the like identical with the with it being in the last place, right? So it's six choose two again. If you just put the chocolate chip cookie at the end, and if you accidentally have a chocolate chip cookie in the front, then you've got one, two, three, four, five here. So this is just five choose one, five, and a chocolate chip cookie here. You have to subtract that. So that's just five choose one. So six choose two, six choose two. That's six times five over two times two. So that's 30. 30 minus five, 25. Okay. In how many different ways can three men and four women be placed into two groups of two people and one group of three people? If there must be at least one man and one woman in each group. Well, okay, if there are two groups and one group, so there are three groups in total, there has to be one man in each. Are we saying that people are identical? I don't think we can say that. So, okay, um, let's take this to be the group of two. So this is one group of two. This is another group of two. And this is one group of three. So, how do you choose the man for the group of three? There are three men, so you do three. There are three ways to do that. How do you choose the two women who go along with him? Right? Well, you can do four women choose two, so four choose two. Now you multiply it by this. So obviously the other two men are here, but the man, each man. So let's call this person X. Let's call this person Y. Let's call the woman A, B. It doesn't matter which uh, yeah, they're indistinguishable. So it doesn't matter which box you're in. What matters is which woman you're with. So X can either be with A or B. So that's basically two. Same with Y. Y can be with A or B. B can be with X or Y. So that's two. 4 choose 2 is 6. 4 times 3. So 6 times 6, 36 ways. Okay. Our school's girls volleyball team has 14 players, including a set of three triplets. In how many ways can we choose six starters if at most one of the triplets is in the starting lineup? Um, so we can say that none of the triplets are in the starting lineup, which gives us 11 choose 3. Oh, sorry, 11 choose 6. Because then none of the triplets are there, so it's just 11 choose 6. Then we can have exactly one triplet, 11 choose 6. Now, because they're saying that triplets, do we even care like which triplet it is or no? Because obviously with people you're supposed to say they're different, but they're all triplets. Their names begin and end with A, so that maybe they want us to think they're indistinguishable, right? But I don't think you're supposed to do that with people in math, at least. So that's one case. At least we've got that. The other case is, so you do put one of the girls in there, and you've still got 11 people left. So you've got one of the girls and then 11 choose 5. We can put a 3 here, but I don't know if we put it there. I don't know if we're supposed to put it there. 11 choose 6 and 11 choose 5 are the same thing. So it's either 2 times 11 choose 6 or it's 4 times 11 choose 6. So let's just find 11 choose 6 and see. 11 times 10 times 9 times 8 times 7 divided by 5 times 4 times 3 times 2. So we can make this a 3 right away. We can make this um, uh, nothing. We can just remove that completely. Make this a 2. So now there's a 3 here. Now there's a 14 here. So this is 42 times 11. So 424 462. So it's 462 times 2. Because they said that twins. Like if they said just people, then I would put a 3 and I would go with this. But since they said that twins, I want to guess this. If it's wrong, I'll guess this. So times 2. This gives you 8, so 924 for 2. Yeah, 924. That's my first guess, 924. Oh, wait, there might be something else. Never mind. Then I guess it's just the other one. So 1848. But I think it's wrong. I got a feeling it's. Okay, great. So then I don't know why they made it triplets. They could have just said sisters or something. That would have triplets made it confusing. Okay, given the nine-sided regular polygon, so it's just a regular nonagon. How many distinct equilateral triangles in the plane of the polygon have at least two vertices in this set? Okay, wait, this is weird, but basically we can choose any two distinct equilateral triangles. That's just how many possible different lengths can you have, right? So you can pick A1, um, A1, A9, and A1, A2 are the same. A1, A3, and A1, A8 are the same. A1, A4, and A1, A7 are the same. So they're four. I think it's just four different, like, non-congruent, non-congruent ones. I think that's what they're asking because let's draw it out a bit. One, two, three, four, five, six, seven, eight, nine. So it looks something like that, right? Let's say this is where you're starting. It doesn't matter. It's arbitrary. But either you can have something with this length, you can have something with this length, you can have something with this length, or you can have something with this length. So that should just be four, but I'm pretty sure that's wrong. Yeah, okay, it's wrong. So how many distinct equilateral triangles in the plane of the polygon? So then they aren't talking about just congruent, right? They must be talking about something else. Well, actually, did I consider everything? One, two, three. Yeah, I think this considers every possible length you can have. Now, for each length, okay, well, this might not be that bad. For each length, you have two possible triangles, right? Like let's say you're starting at some random point. There are four possible lengths. For each rectangle, there are nine possible starting points. And then you can go over to, um, so from that random point that you picked, you can go over to either this neighbor or this neighbor. So that's times two. So there are four possible triangles. Now with this, you can either form this triangle or this triangle, right? Similarly with this, you can either form this triangle or this triangle. Sorry, or this triangle. So there are four possible lengths of triangles you can do, or basically just 9 times 8, right? You can pick this and any other point. So this will just be 9 times 8. You can have this 9 times 8. Then you multiply it though by 2 because there's every point there's this triangle and this triangle. But then note that whether you go from here to here or here to here, those orders don't matter. So you divide it by 2 again. So this cancels to give you just 72. Oh, never mind. Okay, wait. So it seems A1, A4, A7. A1, 1, 2, 3, 4, 5, 6, 7. Okay, this triangle. So any triangle like this seems to have been counted three times. Right, with this point and this point, this point and this point, this point and this point. So it's been counted more. I don't know. Well, 66. Let's just see. There are two equilateral triangles. So there's 72 triangles. However, the three triangles are each counted three times. They should only be counted once. So that's an overcount. And so it's going to be. Okay, I got it. There are three different triangles like that. Each of them are counted three times. And so like the way they're counted three times, it's either with these 2 points, so this point and this point, this point and this point, or this point and this point. Meanwhile, if it's just got two of these sides, then it's just this point and this point. That's only one. Here there's this, three. So that's why you have to subtract it off. But at least we got the 72 part correct. Like we got that part. We just missed this. So okay, not too bad. Now this one. Robert has four indistinguishable gold coins and four indistinguishable silver coins. No two adjacent coins are face to face. So, okay, first of all, you can either have face, then the tail, then face, 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 like that. So, or like people um, lying down on your back and then duplicates on top, or the other way. So that's those are the okay. Basically, the ways you could arrange them, just like which coin goes where, is 8 factorial divided by 4 factorial divided by 4 factorial, or just 8 choose 4. Right? Then you have to also take into account though that each of them can either all of them will be facing the same way. All of them can be facing up. The head can be facing up or down. So that's times 2. Now 8 choose 4 is 8 times 7 times 6 times 5 over 4 times 3 times 2. This cancels with this. This cancels with this to give you 2. So this is 70 times 2, 140. Okay, never mind. It's wrong. No two adjacent coins are face to face. If no two adjacent coins are face to face, the first one is facing up, second one is facing up. That other one can't face on. So they have to be like that. Find the number of possible distinguishable arrangements of the 8 coins. Okay. Did I do 8 choose 4 correctly? Seems right. 8 times 7 times 6 times 5. 4 times 3 times 2 cancel out. 70 times 2 140. Um, what else could be wrong? 140 does seem right. There's 70 possible ways. You can have like all four at the bottom, like gold coins at the bottom, then silver coins on top. The other way, all of them are counted, right? Like if you do 3 and 2, that's it does seem right, but maybe it's 70. I'm guessing that's the other thing that it could be. Oh, never mind. 9. Wait, how? Oh, hi, Logan. I'm doing what I was doing a few days ago, the same thing, but now with counting and probability, not with number theory. I finished that actually. Okay, wait, I skipped the last one. So there are 9 possible ways and then 8 choose 4. So instead of doing 2 times 8 choose 4, what I did that messed it up was 2 times 8 choose 4. Okay. The diagonal of a polyhedron is a line segment containing two non-adjacent vertices. So it's a pentagonal, like a pentagon and then a prism. So it's non-adjacent vertices. So there, how many vertices are there going to be in total? There are going to be 10 vertices. So it's going to be 10. Um, you can't include yourself, right? So the main point, like let's say you're starting at this point over here. You can't include that or the three neighbors. So that leaves you with 4. So 10 times 4 over 2 or divided by 2 because each diagonal gets counted twice. So it's 10 times 4 over 2. So it should be 20. Two non-adjacent vertices. Okay, so 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It leaves with 6. Oh, yeah, no, wait, stupid mistake there. Yeah, because it's 10 minus 4. So I don't know if I did 10. I did 10 times 4. It's 10 times 10 minus 4, which is 10 times 6 divided by 2. So it should be 30, right? Okay, yeah, that was a silly mistake. It's fine. Okay, now this one is irritating. 85 times 84 times 83 over 6. Right, let's just check once in case I made a mistake. 85, yeah. So this is it. If you cancel these two, what do you get? You get 14, right? So it's 85 times 83. Uh, this is irritating. 85, 83. So this will be 64. This is also 64, and then this is 15. This is like a trick that I like to do when I'm multiplying two or three digit numbers. I don't know if you might know it, but I've got another video on my channel. I think I explained it there. 507. So this is what it is. It's this much. Then you multiply it by 14. Right, so to multiply it by 14, 70550, multiply this by 4. So this becomes 220, and then this becomes 28. So 28220. So this becomes 07789. 98770. 98770. Okay. At the end of the year, the math club decided to hold an election for which 5 equal officer positions were available. However, 16 candidates were nominated, of whom 7 were past officers. Yeah, it's better when you're doing it with three-digit numbers because then it takes so much longer when you're doing it normally. It's just a slightly longer process with three-digit numbers. And I guess it's similar with four-digit numbers, but I'm not sure. Okay, the math club decided to hold an election. There are 5 positions. 16 candidates were nominated. How many will have at least one of the past officers? So what if this is complementary counting? So you can just do, so the total number of ways you can order it is just 16 choose 5, right? So 16 choose 5. Then we subtract the cases where you have, I guess you just have to subtract the cases where there are um, 0 past officers, which means there are, so just minus 9 choose 5. Okay, and 16 choose 5. So 16 times 15 times 14 times 13 times 12 over 5 times 4 times 3 times 2. Okay, so this will make this a 3. We'll cancel out the 12, I guess, and we'll make this a 7 to make this 91. 91 times 48. So this is 36, 76, 8. So 8, 6, wait, yeah, 8, 6, 3, 4, 4, 3, 6, 8. I remember I had the same question some time ago. So um, that's fine. 9 choose 5. 9 times 8 times 7 times 6. Well, no, we can just do 9 twos 4 and divide this by. This cancels to make 2. So it's 18 times 7, which is 70 plus what 126, right? So basically it's 4368 minus 126, which will give us 2 over here, 4 2 4 4 2 4 2. Yeah, wait. Yeah, 4 2 4 2 4 2. Okay. Last one over here, I think. An ancient human tribe had a hierarchical system where there existed one chief with two subordinate chiefs, subordinate chief A and subordinate chief B. Okay. Each of whom had two equal inferior officers. Because they've written subordinate chief A and subordinate chief B, I think they are distinguishable, right? First of all, how many people will there be in total? You're basically choosing. Okay, to choose the chief, that's obviously a different position, right? So to choose the chief, there are 10 ways. Then you've got 9 people left. 9 people. From the 9 people, you have to choose. Um. Okay, good. So from 9, you have to choose two. But because they're distinguishable, it's just like 9 times 8, right? So you've chosen these 3 people. Now, for this person, you have to choose two more, two inferior officers, right? And they're equal. And then same with this. So basically, you've got 4 more people to choose out of 7. So it's 7 choose 4. But I think we have to modify that because it depends. Wait, let's do. We can do 7 choose 2, right? And then we can multiply that by 5 choose 2 and multiply that by 2 because this will give. We can pick the first group here. That leaves us with 5 people. So then we pick the second group, and then they can either go this way or this way. I think that's how you do it. 7 choose 2 times 2 is just 7 times 6, like this. And then 5 choose 2 is, well, that's 5 times 1. So that's just another 10. Okay, so, no, there's no 2 over here. I don't think there's a 2 here, right? That should be gone. Because I did 7 times 6 over 2 times 2. So I'm pretty sure this goes. I'm pretty sure. 7 choose 2 times 5 choose 2. Yeah, this seems right. So there's no 2 over there. This is 42 times 72. Again, I'll use the same trick. 28, 22, 4. So 4203, 3024. Again, I saw this somewhere else because I've done so many of these questions. I'm pretty sure the exact same one was elsewhere. And then you just multiply it by that. So 302400. 302400. But this seems like a lot, right? Because, okay, let's try it. Okay, something here is incorrect. Maybe I multiplied it wrong. That could be possible. So there are 10 ways to choose the first person, 8 ways to choose the 9 and 8 ways to choose the other two. Then you have to choose inferior officers. So you do 7 choose 2 times 5 choose 2 to break it up into 2 more groups. Those 2 groups, they're indistinguishable. You're just choosing 2 people and then you multiply it by 2. So 7 times 6 over 2, that. 42 times 72, I've done that correctly, times 100. So something is wrong here. Maybe we have to divide by 2 again. Well, wait, actually. maybe we just, what if we do 7 choose 4? So we've got 10 times 9 times 8 times 7 choose 4. Just to choose those lieutenant people. Like, because they're all, maybe that's the way to do it then. Right? That might make more sense. The number will also be smaller. Let me try it and see. So 7 times 6 times 5 over 3 times 2. Okay, so this cancels. That's just 35. So then it'll be 10 times 72 times 35, which is going to be like a lot smaller of a number. And I think this could be right. So 72 and 35, 21, 21, 35 plus 6. So 35 plus 6 is 41. 10. So 0, 2, 5, 2. 25, 20. I'm not sure because so it says that the inferior people, each they're all equal. So I don't know. What I did before this was say like, just break them up into two different groups and then multiply by two, because this group can either be with Chief A and this group can be with Chief B. But I don't know. So I'm right now I'm just trying by they're all indistinguishable. You just pick the four people because none of them matter anyway, right? So that's what I'm doing here. 7 choose 4 ends up becoming, sorry, when you multiply 9 times 8 and this 7 choose 4, you end up getting 25 20, and then you multiply that by 10. So 25 200, 25 200. That's probably also wrong though. Okay, so they just did, so I was twice as much the first time. It is 10 times 9 times 8, so oh yeah, you can just, I don't know why I multiplied by 2. You can just pick the 7 choose 2 for Chief A and then do it for Chief B. So you don't need to multiply by 2 at the end. Yeah, yeah, you're right. Uh, okay, so you can't put all of them together because what you're saying is right. The lessers under A and B are different, so you have to group them separately. But I multiplied by 2, and that's not needed. So that was my mistake there. So Steve and Danny have to be on opposite teams. Um, that's already given. Then besides that, each team has four people. So we can just put Steve in one team and Danny on one team. Then we know that it's going to be 8 choose 4, right? So 8 choose 4. So Steve and Danny are here. We need 4 more people here, 4 more people here. So it'll be 8 choose 4 to pick, just to randomly pick 4 people, right? So that's 8 times 7 times 6 times 5. 4 times 3 times 2. Cancel, cancel, cancel. 2, 70. So this is 70. Let me just check the work. 8 times 7. Cancel. Yeah, so there's 70 ways to pick one group. Now, that group can either be with Steve or with Danny. And then the other group will have to be with the other person. So we can automatically say that, wait, do we multiply by 2 then or no? We can say that these four people go to Steve and the other four go to Danny. So I think it'll just be 70. Right? You've got Steve on one team. You can say 8 choose 4 will go to Steve, and the remaining 4 choose 4, the remaining people will go to Danny. You can define it like that. Right? Does this work? Or do I have to multiply by 2? We won't divide by 2, that doesn't make sense. But it's possible that we have to multiply by 2. Because, well, if Steve and Danny weren't there, if it was just 8 people going into 4, okay. No, because the groups are distinguishable from Steve and Danny. So since they are distinguishable, we don't need to divide. But we still, but we don't multiply either. Because if Steve and Danny weren't there, it would just be 8 truths for over 2. And now because they're distinguishable, it's 70. So I'm putting that in and seeing. Okay, good. What is the value of n? There are a total of 120 triangles. Okay, so yeah, 70. Good. So we got it. The figure below represents a figure with a total. So if it's 120 triangles in total, P is obviously a part of it. So you just need two more triangles at the bottom. So n choose 2 should be 120. Right? N choose 2 should be 120, I think. So n times n minus 1 is equal to 240. So n is just going to be 16. Okay, let me check though, like just generally, like if you had 4, if n was 4, then you'd have n choose 2, which is 6, right? 6 triangles, because it would be, this is 1 triangle, 2 triangles, 3 triangles, 4, 5, 6. Okay, that seems right. So I'm going to put 16 in. If it's wrong, then we'll retry. Okay, perfect. Good. Got this. At the grocery store, I bought 4 different items. I bought 3 identical bags. Oh, wait, we're done with combinations and restrictions. So this is distinguishability now. 4 different items, 3 identical bags, and handed them to the cashier. How many ways are there for the cashier to put the items I bought in the 3 bags? So he could leave them empty as well, right? So basically, 4 different items, 3 identical bags. So that's like having. So how many ways are there? Like, right, one of them you can have 400. You can have 310. You can have 211 or 210. Sorry, or 220. Then with 1, well, we've done that. You can have 1 and 3 or 1, 1 and 2. And then obviously, it doesn't matter where the 1 is, right? Like that shouldn't matter because these are all indistinguishable. So these are the unique possibilities you can have. With this, there's only one way this can, wait. So wouldn't it just be 4 or, okay, this would be 1. This would be 4 because there, you can choose like which one is going to be isolated. Over here, which one is going to be, so it will be 4 choose 2 over here, right? Because you have to see which two of them will go in a group of, like which two of the 4 will go in the group of 2. The other 2 will obviously be isolated. So this is 6. And similarly, this will also be 4 choose 2 because you just pick like which 2 will be together, which 2 will be together. So this is also 6. So this adds up to 10, 17. So I think it's 17. If wrong, then we'll go over it again. Okay, this is wrong again. So let's see. Am I missing anything? 400 works. 310 works. The bags are 3 identical bags and they're 4 different items. So over here, it doesn't matter. All 4 will have to be in one bag. Over here, you can have 3 in one bag and 1 in one bag. And the way to decide which 3 go where and one bag, so which one is isolated, there are 4 ways. Then with 2, you can have 211 or 220. In 220, it's enough to say 4 choose 2. Maybe this one is actually like 12. Let me see. So 4 choose 2 gives you 2 people who are going to be together, and you know the other 2 are divided. So actually, wait, this seems right. So I think I'm just understanding the whole concept wrong. If I'm getting, if that isn't right. 4 different items. So since the bags are identical, you can have 4 over here, 0 here, 0 here. There's only one way to do that because all 4 items will be going somewhere. Or you can have 3, 1, 0. It doesn't matter if this is 0, this is 1, or if this is 1, 0, 3. None of that matters because they're all identical bags. So what matters here then is like which 3 do you put here? Do you put the circle, the diamond, the square, and the triangle over here? Do you put the triangle here? Wait, 1 second. I'm getting called away, I think. Okay, back now. Sorry about that. Okay, so let's look at it again. Four different items, three identical bags, and so it is possible that some of the bags are empty. But what if, okay, four different items, three identical bags, and hand them to the cashier. How many ways are there for the cashier to put the items I bought in the three identical bags, assuming he can leave them empty? So he can obviously here he's left two of them empty. Here he's left one of them empty. With one, I think we've already covered those cases, right? With 1 3 0, that's done. 1 1 2 is done as well. 1 1 2 1 3 0. Besides that, there's really nothing else that can happen here. So it must be this. That's the error. With 4 0 0, I'm pretty sure that's correct. With 3 1, that should also be right because it's just like how many. So 4 0 0. There's only one way that can happen. You put all of them in one bag, or you can put them in two different bags with three in one and one in another, and that will be four cases. Or you can put one, one, and two. Now, these two don't really matter. What matters is how you can pick the two items that will be together, because the other two will obviously be separate. The way to do that is for choose two. Over here again, we have to basically break it up into two teams. So it'll be this. Oh wait, this is for choose two over two because it's okay. I think that's a mistake then. Because you're picking two things, you have to divide it by two. That's probably the only. I think that's the only thing that makes sense as to like how I messed it up this far. I think this has to be my mistake. So then you add these up, you get 14 instead. I'm pretty sure that's right because everything else seems correct. So it's hopefully 14. Okay, yeah. Two items go in one bag and the other two items go in a different one of the remaining bags. There's six ways to choose which two items are put in a bag together. Yeah, okay, so case 4 we did that correctly. Case 1 obviously correct. Case 2 is also fine. Case 3, there are six ways to choose which items go in the first bag, but since the bags are identical, we divide by 2. That's a mistake. Okay, Ben throws four identical darts. Each hits one of the four identical dartboards on the wall. After throwing the four darts, he lists the number of darts that hit each wall, from greatest to least. Wait, he throws four identical darts. Each hits one of four identical dartboards on the wall. He lists a number of darts that hit each board, from greatest to least. Isn't it just 1 1 1 1? I'm pretty sure I'm misunderstanding the question because if you throw four identical darts, each hits one. Oh, they aren't saying each doesn't hit one. Each hits one out of the four, and you don't know which one out of the four. So basically, all of them could hit one. So it can be four, or you can have three and one. Okay, yeah. So basically like this. So that this is one dartboard, one dartboard, one dartboard, one dartboard, and then it can either go. So they can all go like this or like this, and then basically they're asking how many different lists are possible. So obviously you can have 4 0 0 0. Then you can have 3 comma 1. That's also possible. You can have two and two. Then the other two will obviously be zero. This is the exact same as the last one in terms of the numbers. So there should just be four. You can also have 2, 1, 1, 0. So this is just four different ways. 4, 0, 0, 3, 1, 0, 0, because you're doing it in from greatest to least in descending order. So the odd. So this is it. I'm going to put in 4. I'm not 100% sure, but come on. Wrong again. So is something here not possible? Four identical dots. Each hits one of four identical dot words on the wall. Oh wait. I Never mind. There's also one, 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 one. In the last one that wasn't there because there were only five things, and that's what I messed up here. You can have 4, 0, 0, 0, 3, 1, 0, 0, 2, 2, 0, 0, 2, 1, 1, 0. But you can also have 1, 1, 1, 1. So that'll be 5. That's missed that. The numbers aren't the same as the last one. So that was I said that wrong. Okay, this one. Well, we can just take out the 10 factorial and the 11 factorial, I think. Right? We can just say, or we can just factor out a 10 factorial from everything. So it's 10 factorial plus 11 factorial plus 12 factorial over 10 factorial plus 11 factorial. We could just like take out 1 and then do 12 over 10 factorial plus 1 factorial, or we could factor out a 10 factorial from everything, which seems a bit better. So if we do that, they'll cancel out. So we get 1 plus 11 plus 132 over 1 plus 11. This becomes 143. So 144 over. So I'm just getting 12 here, but that seems like it could be off. Let's see. 12. Yeah, that seems right actually. Okay, so you just factor it out and simplify it from there. Henry's little brother has 8 identical stickers and 4 identical sheets of paper. How many ways are there for him to put all of the stickers on the sheets of paper if only the number of stickers on each sheet matters? So it's all identical. Again, it's the same number thing. Okay, so you can have like, there must be a faster way for this, but you can have 8000. Then you can have 7 and 100. You can have 6200, or you can have 6110. So we now with 5 you can have 5 and 300. You can have 521. I'm going to skip the zeros now because they're not really helping. Actually, let's restart the whole thing without any zeros, just to keep it a bit more organized and neat. Okay, so you can have 8, you can have 7, 1. Basically, we just need to add up to 8. Right? How do you add up to 8? 6, 1, 1, 6, 2, 5, 3, 5, 2, 1, 5, 1, 1, 1. Um, the important thing here is that, so with 8 there's only 1, with 7 there's 1, with 6 there are 2, with 5 there are 3. So is it safe to assume that with 4 you'll again have but actually we only need to calculate until 4. 4 and 4, 4, 3, 1, 4. We can change the 3 now to make it a 2, 1, 1, or make the 3 just 1, 1, 1, and that's it. Never mind, actually, never mind. There are 4 sheets, so we can't go that far. 4, 3, 1, 4, 2, 1, 1. That's it. You can't have 4, 1, 1, 1. So this is it. Again, you've only got In fact, here you've only got three again, so not four, just three. If you have three, the others need to add up to five. So you either have four and one, you have five, or you can have. I guess you can have three. Let's continue on the right here. This is also one, by the way. So all of these are obviously possible, but you can also have three, three, and then one, one, or three, three, two. Three and five is already done, so I'm not going to count that again. Same with three, four, one. But that's it. You can't have. Oh wait, or you can have three, three, one, one, and that's it. So there are three more of these. With two, we've done I think everything with two. Two and six, two and five and one, two, four, one, one. What about two, four, two? In fact, what about uh, not good. We also had 422 over here. So let me put that in here instead. 224 works. 251 doesn't work. 260 doesn't work. 224. What about 2411? That's already done. So now we go down to 2 and 3. We've got 233, or we've got 2 3 2 1. 233 is already done. That's why. So this is 2. And then I think with 1 now we've done like everything. 1 would have a total of of 7, and it's 1. So wait, didn't I just repeat this then? That's not right. 3311, 332. So that's obviously wrong. I can't do that. So this should also be 2 then, I guess. Not sure. And we've done all the ones. We've done 1 and 7. We've done 1 and 6 and 1. 1 5 1 1. 1 5 2. 1 4 3. 1 4 2 1. What about 1? Yeah, that's it. With 1 3, then you've got 4 left. So 1 3 3 1. 1 3 2 2. 1 3 4 0 done. So I think that's it. I'm actually I've done this question very badly, so very possible I've made mistakes here. Also, I need to zoom out a bit for you. So let's see, what is it? It's 1 1 2. That becomes 4. So this adds up to 10. So it adds up to 14. But there's definitely a smarter way to do it. Okay, it's wrong. So 1 2 3 4 5 6. So you know what? We should probably leave these and just be more comprehensive on the left. That's probably better. 5 1 1 1. We've done that. We've done everything with 5. I think we messed up with 4. That's why we made some mistakes. Because 4 2 2 works and we didn't put that. So that was one mistake over there. 4 2 2. What about, well, is that it? That might be it. Similarly, 2 3 2 1 should have gone there. Oh, wait, no, this isn't it. We still need to incorporate some more stuff. Like, 3 3 2. Stuff with only small numbers still has to be done. We also just missed. Well, actually, let's continue with what we did because I think we've done basically everything. There's one more possibility here, though. We can just have 2 2 2 2. It's just not an organized way of thinking about it, so I don't like it much. But maybe it's 15. Well, then I'm sure there's another one that I'm missing completely. That could be there too. Let's just guess 15. If it's wrong, we'll see what's. Okay, good. 800. Okay, they just listed them out. Okay, so that's what we did as well, I guess. Two identical basil plants and an aloe plant. Uh, Aloe vera. Right, that's what it is. Okay. She also has two identical white lamps and two identical red lamps she can put each plant under. She can put more than one plant under a lamp, but each plant is under exactly one lamp. So she's got four lamps. Okay, first of all, we can make white and red, white and black. So let's do that here. This becomes your white one. This becomes your other white one. This becomes your black one. This becomes another black one. So now what all do you have? You've basically got, what is it? You've got, let's call the plants star, star and triangle. Okay, so you can have something like this, zero, like this. Um, okay, first of all, let's see like what happens when you've got three. One plant has three. So here you can either have this or this. There are only two combinations for this. So when a plant has three, sorry, when a lamp has three, two possibilities. When a lamp has two, then what are the possibilities that you have? It'll be a bit more, I think. I think it'll be four, but I'm not sure yet. So first of all, lamp has two. First of all, you can have the two. They can either be two circles or a circle and this, right? So that's two possibilities. That will also define what the other one is. Okay, then on top of that, these two can be under a white or a black lamp. So there are two possible sets of two. There are two possible lamps that they can be under, and there are two possible lamps that the other one can be under. So that's eight. Last case, if a lamp has just one, so each lamp has one. Um, so basically now, let's erase it. Basically we can have circle, circle, and then triangle like this. Okay, the triangle can either be black or white, right? It can either be black or white. Let's say it's black. Then the other two can either be white or one white, one black. So the triangle is black or the triangle is in black. This gives you two cases. You can either have both being white or one white, one black. And it'll be the same if it's the other color. So that should be four ways. So if you add all this up now, you get 14, which is, oh, perfect. And we got that right as well. Let's just read what they did here. Okay, all three, so exact same process as well. Basically the same thing. Okay, how many ways are there to put four distinguishable balls into two distinguishable boxes? Okay, this is going to be much, I think it's going to be lengthier and harder. Wait, no, actually, there are four balls, right? And there are two boxes. So in each box, for each ball, you can either have two to the, you have two choices. So you can either have it go in this box or this box. So it's 2 times 2 times 2 times 2, 2 to the fourth, 16. I'm pretty sure that's it. This is the easiest one. Yeah, perfect. Distinguishability done. Basic probability as counting. Okay, now we're like, I think definitely halfway done. Let me see. How many things are there in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we've done 13. In total, there are 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So I think they're like 27 or 28. So we're not quite there yet. We're not halfway there, but we're close. Not too bad. Correcting for overcounting with division. If we do these two, then we'll have like over half done. But let's do multiplying probabilities. Let's do something else that might be easy. So the first one is going to be 7 out of 10. Like the probability that the tile from box A is less than 15. That's 14 out of 20. So 7 out of 10. Tile from box is either greater than 25 or even. So you go from 12 until 24, which is, sorry, not from, yeah, from 12 until 24, which is, what the hell? Oh, so that's 6 until 12. So that's 7 numbers. And then obviously, or greater than 25. So you've got 26, 27, 28, 29, 30. So that becomes 12 out of 10, which is 6 out of 10. So 42, no, well, 6 out of 10 is 3 out of 5. So it's 21 out of 50. Okay. If Ella rolls a standard six-sided die until she rolls the same number on consecutive rolls, what is the probability that her 10th roll is her last roll? So, oh, okay, wait. So you have to get, you can get anything on the first one, right? Then you have to get, so the first roll, second roll, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. So you can have anything here, right? Like literally anything. Then though you have to get a 5/6 of not getting 5/6 to get anything else. Again 5/6 to get anything else, and so on. This is going to happen 8 times, so 5/6. Then at the end, whatever the last one was, there's a 1/6 chance, so you have to get that. So it's 5/6 to the eighth. I'm putting this in a calculator and seeing, divided by 6. Right, let's see what that is. 0.039. Right, because I don't want to actually calculate that thing to the nearest thousand, so it'll be 0.039. Yeah, and I'm pretty sure they used a calculator as well for this, because that's no need to actually calculate that stuff. Erica, who's 14 years old, flips a fair coin whose sides are labeled 10 to 20, and then she adds a number on top of the flip coin to the number she rolls on a standard die. Standard die means six-sided dice, right? So, or six-sided die, whatever. So there's a half chance that it's impossible, because there's a 1/12th chance. The halfway, you have to get a 10, basically that's already a half chance. Then you have to get a 4, which is a 1/6. So it's 1/12. Okay, batting average is 0.323. What is the probability that he will get 3 hits in 3 at bats? So you just multiply that again and again and again. 0.323 cubed. Because it's just like, oh sorry, 0.323 cubed. So 0.03. They turn out they turn out with probability 1/5. So basically 1 minus 4/5 to some power is greater than 3/4. That's what we have. 1 minus 4/5. Well, we can actually just figure this out, right? We can do add this here and subtract that. So you get 1/4 is greater than or equal to 4/5 to the n. We can actually make this even easier. So you have 5/4 to the n is greater than 4. So you can have like, if you have 3, you have 125/64. Obviously not that. But this is almost 2, right? Think about it. 128 over 64 would be 2. This is cubing it. So you can raise it to the seventh power. That will take you that will take you there. So 7. You need 7 of them. Great. Multiplying probability is done. I think we're like now halfway done. Probability, think about it. Let's see these. That's 0 because exactly 4 people can't get the right one. Then the fifth one would also have to get the right one. A box contains exactly 5 chips, 3 red and 2 white. Chips are randomly removed one at a time without replacement until all the red chips are drawn or all the white chips are drawn. What is the probability that the last chip drawn is white? Uh, because it's probability, think about it. I'm going to guess it's just half. Okay, it's wrong. Um, so maybe it's 2/5 then. Because 3 red. So yeah, 2/5. That's my guess here. But it says think about it. So I think you're not supposed to calculate anything. Just um guess, like just think about it logically and do it. Okay, let's see. Therefore, the probability that the last chip drawn is white. Oh, you just list out all the orderings. Okay. Imagine drawing until only one chip remains. If the remaining chip is red, that draw would have ended when the second. Okay, fine. Carson flips over the cards of a standard 52 card deck one at a time. What is the probability that he flips over the ace of spades before any face card? You could either flip the jack, queen, king, or ace first, right? So there should be a 1/4. Oh, ace of spades before any face card. So what's the ace of spades? It would be 1/4 divided by 4, maybe 1/16 then. Because there's a 1/4 that you. What? There are 12 face cards, 3 from each suit. How are they 12? Shouldn't there be. Oh, before any face card. So they're 12. Okay. I'm doing very badly here. The Badgers play the Cougars in a series of 7 basketball games. Winning at least 4 games means that you win the series. So that should be a half chance for that. When two consecutive whole numbers are randomly selected, what is the probability that one of them is a multiple of 4? So, obviously, one of them will be a multiple of 2. So, it's a half chance. One of them, two consecutive whole numbers. So, it'll either be a multiple of 2 or a multiple of 4. 4 points A, B, C, D are chosen randomly and independently on the circumference of a circle. What's the probability that segments A, B, and C, D intersect? We can just draw it and see, right? This one, let's take these as our points. So you can take this, if you take the ones that are opposite each other, right? So this, there's a 1/3. If you take this, they won't intersect. If you take this, they won't intersect. If you take this, they will intersect. So there should be a 1/3 chance of that. Let S be the set of all sides and diagonals of a regular pentagon. A pair of elements S, a pair of elements of S are selected at random without replacement. What is the probability that the two chosen segments have the same length? Okay, what's the probability that they don't? That will be half if you choose one diagonal and one side. Oh wait, the diagonals aren't the same. All the diagonals won't have the same length, right? Or will they? I think all the diagonals will have the same length. They'll all be this long. So then there's just a one half chance. Never mind. All sides and all diagonals. How many diagonals are there? Well, n times n minus 3 over 2. Are there just 5? Yeah, I think that's it. There are 5 diagonals. So you can either choose a side or a diagonal. Diagonals and sides are not the same length. So there's a one half chance that you choose whatever you choose. There's a one half chance. Let's say you choose whichever thing you choose, either a side or a diagonal. There's a one half chance that you choose the other thing, right? Then they won't be equal. But anything else, they will be equal. So it should just be one half. Whether you get a diagonal and a diagonal, those are all the same. Oh, without replacement. Hmm. So in total, there are 20. Sorry, in total, there are 90 things without replacement. I think that changes it up a bit. In total, there are 90 possibilities. You can either get, if to get what you want, it's going to be 5 times 4. So that's 20 plus 20. So it's going to cancel out to give you 4 over 9. Max picks 2 different cards without replacement from a standard 52 card deck. What is the probability that the cards are of different suits? Suits are the colors, I think, right? Like, not colors. It's like spades, hearts, diamonds, clubs. It's like that. So what's the probability that the cards are of the same suit? That's one fourth. So it'll just be three fourths then. Wait, no, 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 no. What is the probability that you get the same thing? It'll be 12 out of 51, right? Won't it be that? Because you take one without replacement. Yeah, so you take one and then you've got, and this is just 4 out of 17. So it'll be 13 out of 17 then. 1 minus that. Okay, done. We got that done as well. Let's see. And now I'm actually thinking we can do, it's not that bad. We're close, I think. We're definitely over halfway done just on the looks of it. Let's see. Can we do anything here? Like maybe geometric probability? That could be something. Two real numbers are chosen at random between 0 and 2. So it's going to be pi out of 4, I think. If you draw a circle, yeah, that's what I was saying. You draw a circle, you cut it into one fourth, like into the sector in the first quadrant, and it's out of 4. So it'll be 2 pi squared whole squared over 4 over 4. Okay, a point P is randomly placed in the interior of the right triangle below. What is the probability that the area of P? So basically BC, AC, PC. PC has to be half of AC. If it's so, it should be three fourths then, right? Okay, good. The way I did that was because you need PC to be in the bottom half of the triangle, and that's a similar. The top half is the similar triangle with one fourth the area, so it's three fourths of the area. So it's three fourths. So we're given a rectangle 0, 0, 4, 0, 4, 1, and then that. What is the probability that x is less than y? That's great. We can just draw it out, right? So 0 to 4 and then 1. So this is 0. This is 0 comma 4. 0 comma 1, 4 comma 1. This is our rectangle. We want x out of, okay, this height is 1, this is 4. X is less than y. Um, So wouldn't that so you just draw this out like this? This well, it's kind of it's not drawn to scale, but it'll be like this. Whatever the intersection is, it'll be 1 1. Sorry, yeah, 1 1 is the intersection of x equals y. X is less than y, which means basically y is greater than x. So it'll be this section here, right? It's not drawn to scale, but this is 1, this is 1. So it's 1/4 out of 4. Sorry, 1/2 out of 4, which is 1/8. Yeah, I didn't draw it to scale, but the idea is the same. Okay, John needs to catch a train. The train arrives randomly sometime between 2 and 3, waits for 20 minutes, and then leaves. I remember, I took an AOPS class once. This is geometric probability, right? So it was the same thing, and they gave like very similar questions to those. Then they had something just like this. So I remember the train thing. I remember that they taught me this. I don't remember how to do it. So let's see. The train arrives randomly sometime between 2 and 3, waits for 20 minutes, and then leaves. So I remember it's like this, right? It arrives sometime randomly between 2 and 3. But let's see if we can. Okay, let's draw it out then. I think that's what you're supposed to do. So this is the axis here. You've got 2 o'clock, you've got 3 o'clock. It'll arrive at some point there and it'll stay for 20 minutes. So I maybe I'll have to see the solution and do it after that because I remember how it works. Um, I don't really remember how it works. Let's see. It's just going to be some fraction. Well, okay. So let's say that this is the train and this is John, right? This is John. And then this is the train. So the train is going to arrive. It's this is 1/3. So and it's got a slope of 1. I think this is kind of what it's like. This is going to be 2, this is going to be 3. Or not that much. Maybe 2 is here, 3 is here. So John is here, right? And the train is, I think this is also 1/3, right? Or no, this has to be 2/3 then I think. 2/3 and 0. Never mind. Wait, this is wrong. The So at 2 it will be, let's just change this a bit like this. Okay, now 2, so 2 should be like right here. 3 should be like right here. I think it's represented by this. Okay, so 2 meaning it's like this. You know what, I don't remember at all. Let me just see. John has to get there within 20 minutes of the train getting there, basically. So if whenever the train comes, John has to get there within 20 minutes of that. If John gets here at 3, the train will be gone. Well, let's see. The train will stay for 20 minutes, right? This is If the train comes at 2 o'clock, it's going to stay there until 2 o'clock. So this is 3. Okay, you know what? I don't really know. This total area is 1. We're going to go with this. This is the intersection of when John and the train will meet. So here and no, actually over that John and the train won't actually meet, right? They meet on a shorter time frame because if John gets there before the train, think about it, then he's not going to ever see the train. So there's already a half chance of that. On top of that, if he gets there within so there's half of that. Then there's a half chance that he gets there 20 minutes after the train. Let's say the train gets there so it's going to be less than half, which means obviously this is what we're looking for. This completely black area. So this goes from 2 to 2 equals 1/3 until so it's not drawn to scale. That's making it harder to understand. Much harder to understand. In reality, like 3 should be right here, right? Something like that. So it'll be like this. What are we looking for here? So this is going to be 2 and 1/3, which means this height is 2/3, which means this section here is going to be all, I'd say also 2/3, but I'm not 100% sure. Yeah, this should be at 2 and 2/3. So 2/3, 2/3. 4 out of 9, 4 out of 18, meaning 2 out of 9. I think there's a 2/9 probability. Yeah, okay, that's wrong. So let's try 4/9 and see. Okay, this is what I wanted to see because I knew it was some shape like this. We put the time the train arrives on the y-axis and the time John arrives on the x-axis. The probability that John arrives while the train is at the station is the ratio of the shaded area to the whole square. So it's 5 out of 18. What did I say? I got 4 out of 18. Maybe I was supposed to subtract that then. Oh, wait. So it's like this, but in reality, we're supposed to find the area of this. Right? Like instead, we found this to be 4/9. We needed, this is the mystery area. This is probably what we were looking for. Okay, well, let's see how they've graphed it though, how they've drawn it. So the train is on top. If the train gets there at 2 o'clock, it'll last until 2:20. If it gets there at 3, then nothing much. But okay, so that actually does make a lot of sense then. Hmm, fine. Now this is something I've never seen before. Green for 30 seconds, then yellow, then red. What is the probability that the color changes while she's watching? We can try a similar model to the last one, but this is a bit harder actually. Let's see. Let's see. Let's just draw something, okay? So 30 seconds here, 3 seconds here, so 33, 63. So until here it's like at this height, right? Then suddenly it goes up to this height. Then suddenly it goes up to this height. So the chance that you'll see one of these happening, well, she picks a random 30-second interval. Okay, okay. So she can come with 3-second interval, sorry. So from 27 here, because this is a 3 second interval, even this is fine, you'll still see it. That'll work the whole time, and it'll go until here. So what all works? You've got from 27 until 36. So that's 9 seconds out of 63, right? And then again, and then it'll continue. I think that's it. But let's draw a bit more. This so that's 1/7. That's what I've got so far, but that could very well be wrong. So let's see. Let's see if the ratio continues if we do it again. Then you go here, here, here. So this becomes 93, 96, 1, 126. Oh wait, no, I'm just missing it, right? Because it's not just this. It's so out of 63, all of this works. But then think about it. This second range also works, right? This is another 3 seconds, and this here is another 3 seconds for which you will see it. So from 27 to 36 plus these six. So this is 9, 12, 15. 15 out of 63. If you take out a 3, you get 21 and 5 over 21. So it should be 5 over 21 then. Come on. How is this wrong? So okay, 27 works. Obviously that will work. Then 30 obviously works because that's when it's changing. 33 will also work because that will also work. Anything between 30 and 33 will work. It goes until 36. Oh wait, no, it doesn't. Never mind. Never mind. So 27 will work all the way until here. After that, it doesn't work because it's not happening after that. Same with this. This doesn't count either. So this will work because in the next 3 seconds it happens. The previous 3 seconds don't matter. So this entire range will work. This is 3 seconds. This is another 3 seconds. Uh, this works. So 333, 9 out of 63, which is indeed 1/7. So that should be right. Great. A coin that is 8 centimeters in diameter is tossed. A coin is in a winning position if it's like this. Coin is in a losing position if it lands like that. Hmm. So we're given that it lands somewhere in the grid. What is the probability that it's in a winning position? So basically the diameter has to be in the sweet spot, right? The diameter is 8/10. So there's an 8/10 chance that it's located inside properly. Sorry, no. What's the chance that it's hmm. So it's basically like this in a square, right? This is this thing is 8. This thing is also 8. So it's going to be some square. I know that. Um, and basically you have to have it so that the 8, it can go from, you can go from right here, which doesn't work. And so you're starting at -8. And you can go until right here, which basically doesn't work, right? Those are the limits. Until this is 10. So this is um 0. So -8, 0, 10, 18. Until 18. And it's the exact same in the height, right? So out of 26, how much of it works? It's 10 out of 26 or 5 out of 13, right? 5 out of 13 chance that you're in this range because anywhere here it doesn't work. Same in vertically. So it'll be 25 out of 169. Is it 1 minus that? Did we calculate something wrong over here? I think that might be the case. Not sure, but no, wait, it's not until there. But let's just look at the left side here, right? We don't go that far. It's out of 5 out of 10 out of 18 because this can go here. The left side can be from here. None of this works. None of these 8 work. Then here it does work, and here it works for 2, and then after that again it stops working. So it's actually 2 out of 18, 1/9. Square that and you get 1 out of 81, right? Because you have, so let's draw it again here. We can't, here we went from the left edge and here we looked at the right edge. That doesn't even work, right? Maybe it does, but I don't know. Over here, meanwhile, if we go with 8, so just look at the left edge. The left edge can be anywhere from -8 to 0. That won't work. Then from 0 to 2, it will work. Anything after that, and again, it will go out. So it's 1/9. Out of, like, this entire length is 18, and only this 2. So that 1/9 of it, only 1/9 of it works. And it's the same in the vertical direction. So it should be 1 out of 81. That's wrong as well. Oh, well, I guess that's because it's 5 grids, right? Maybe that's what you have to look at. See, a lot of these questions are much harder than my class ever went into. So let's see. Since this grid is a 5 by 5 grid, since the diameter the radius of the coin is 8, the radius is 4 centimeters. Okay, no, so it's not out of 2500. It'll be out of 1764 because they said it's not off the grid. So it has to be somewhere in there anyway. Consider one of the 25 squares. Okay, they just looked at the center, right? It must land in the region of 100, so it's 100 out of that. 25 out of 441. So not even close to what we got. Ours was way less than that. So they each arrive at a party at a random time. If Alice arrives after Bob, what is the probability that Bob arrived before 1:30? So you can have so what's the probability that hmm, so this is from 1 to 2, 1.5. We know that Alice came after Bob. This means that the probability that Bob came before 130. So if Alice came before him, that would mean Alice is here and Bob is here. So in this one half, that's a one-fourth probability. The probability that Alice came after Bob. Wait, wait. Let's look at the complement of this. What's the probability that Bob Alice comes after Bob? What is the probability that Bob doesn't come before 130? That means he comes after 130, right? That means that both of them are in this one half range. So one half times one half, which is one fourth. So it'll be one minus one fourth or three fourths. So from negative 1 to negative 1 to negative 1. What is the probability that x squared plus y squared plus z squared is less than or equal to 1? So it's like a sphere with radius 1 out of a cube with radius 1. So it's out of 1, it's just the volume of a sphere. 4 thirds pi. No, never mind. Yeah, it's out of 8 then because the lengths are all 2. So it's 4 thirds pi out of 2 cubed, which just becomes pi over 6. Okay, come on, just one more right, and that will be enough. Okay, given that a and b are real numbers such that negative 3 is less than a is less than 1, we can just make that those x and y, that should be fine. So it's from negative 3 to 1, and negative 2 to 4. So negative 2 to 4. So it'll be something like this. So what's the probability that the product will be positive, right? This height here is 6. This length here is 4. So it's out of 24. To be positive and positive, it's going to be this section, which has, this is 3, this is 3. So this is 9. And it's going to be this section, which has height 3, and this is 1. So this is 3. So it's literally just a 1/2 then. Never mind. Wait. Uh, Negative 3 to 1. We've done that correctly. And negative 2 until 4. Oh, wait, sorry. This is what I did wrong then. This height here is actually 4, right? Because this height is 2. Wait, what am I doing here? This height is 2. Negative 2, this is 1 comma 0. I should include that stuff. 0 comma negative 2 here. Or sorry, 1 comma negative 2. I need to include coordinates here. So this height is 2. Okay, new information. This is 2. Negative 3 to 0. So this is still 3. So this is now 6. The total area, I think, is still 4 to negative 2. So this is 6, this is 4. So it's still out of 24. Now, though, over here we've got this height becomes 4 and this becomes 1. So this is now 4. So it's 10 out of 24 or 5 out of 12. So this should be 5 out of 12. Alex needs to catch a train. Okay, this is the same exact thing, but now with 10 minutes instead of 20 minutes. So let's do it, and let's do it right this time. So I think we put Alex at the bottom and the train on top on the left here. What timings do we have here? 1 and 2. So 1, 2, 2. The train will basically go like this. Sorry, like this. So we need this area over here. Note that this is now 7/6, which means that this part is 5/6. This is 5/6. Yeah, because it's 5/6. Sorry, I know I'm sounding weird right now, but that's fine. So this is 5/6, meaning 25 out of 36 or 25 out of 72. Um, 25, no, wait. Yeah, so this part is going to be 36 out of 72, which is one half, minus 25 over 72. So 11 out of 72, right? A hi guy from call center. Because it's half and then minus that. So 11 out of 72. Good. Now we're done with that. Expected value. Okay. Um, we won't do expected value right now. We've already done like, well, now it's like well over half of all of counting and probability today. So we'll continue this later after dinner now. So, well, thanks for watching. We'll do more of this later. It's been, I think this is now probably the longest stream so far. It's already been over 3 hours, just over 3 hours. So we should, um, I'll see you guys tomorrow then. Or and maybe not tomorrow, maybe later. Bye.